Hi everybody. So today's video is going to be about lesson 8 from unit 1, which is connecting the idea of a limit with the idea with infinity. So the learning targets for today are I can identify the locations, if any, of the vertical asymptotes of a function. So one of the things we're going to be looking at today when we connect infinity and limits is vertical asymptotes. The second learning target is I can evaluate limits as x approaches positive or negative infinity. So we're looking at x approaching infinite values. And finally, I can identify the locations of horizontal asymptotes of a function when they exist. So we're also, in addition to vertical asymptotes, going to be examining the connection between limits and horizontal asymptotes. So let's just start with a review of what we've learned as far as algebraic limits. What we have learned is that just because a function is undefined at a particular x value does not mean that the limit does not exist at that value. For example, if we were to try to evaluate the limit given here, our first step would be to try direct substitution. Now, if we try direct substitution, we're going to get 2 squared plus 2 minus 6 over 2 squared minus 6 times 2 plus 8. If we simplify the numerator, we get 0, and if we simplify the denominator, we get 0. So we said that this is what is called an indeterminate form of a limit. As a result, we said our next step here would be to try factoring to simplify this limit and then try substituting again. So if we were to factor here with this limit, the limit as x approaches 2, we would have x plus 3 times x minus 2 over x minus 4 times x minus 2. What we should notice here is that the x minus 2's cancel in both the numerator and denominator. So now, if we were to try substituting the number 2 into our new function, we would have 2 plus 3 divided by 2 minus 4, which gives us 5 divided by negative 2, which is our answer. So again, going back to what we started with here in this box, we've learned that just because a function is undefined, so we tried to substitute and it didn't work, does not mean that the limit does not exist. It means that we might have to do a little bit of work before we can figure out the value of the limit. In this example, we can see that direct substitution gives us 0 over 0, which we considered an indeterminate form. After factoring, we can see that the graph of a function will have a vertical asymptote at x equals 2. Oh, I'm sorry, not a vertical asymptote. That was my bad. It's actually a hole at x equals 2 because those factors cancel, which was the next thing I was going to talk about. We're going to have a hole there because the factor cancels from both the numerator and the denominator. When we resubstitute into the simplified function, we find that the value of the limit is negative 5 over 2. Now, it turns out there's one more piece that we need to consider here in this problem. What happens with the x minus 4? For example, if we had changed this limit and we said the limit as x approaches 4 instead of the limit as x approaches 2, even though these factors would have canceled, the x minus 4 would not have canceled. So we would still not have been able to substitute successfully. That's what we're going to look at next, is what is happening at x equals 4. So we know that there's a hole at x equals 2 because that factor canceled. A vertical asymptote occurs when the denominator of a rational function is equal to 0, and that factor does not cancel. So when we look back at this equation where x minus 4 does not cancel, instead of having a hole at that location on the graph, we would have a vertical asymptote. Now there are 3 things that can happen surrounding a vertical asymptote. We could have a vertical asymptote like the one showed here, where the 2 sides of the graph as they approach the asymptote both head towards infinity. We would say that both one-sided limits approach infinity, and therefore the two-sided limit exists. And the reason that the two-sided limit exists is that the two one-sided limits agree, so we would say that the two-sided limit's value is infinity. A second situation could be that near that vertical asymptote, the two one-sided limits both go down towards negative infinity. So because of that, we would say that the one-sided limits both approach negative infinity, which means the two-sided limit exists again, it's negative infinity. The third situation that can occur near a vertical asymptote is that the one-sided limits go opposite ways. In this case, I'm showing you an example where the limit as x approaches the asymptote from the left is positive infinity, and the limit as x approaches the asymptote from the right is negative infinity. Because of that, we would say that the two-sided limit does not exist. Now, this is important because it tells us that whenever there is a vertical asymptote at a certain location in a function, we need to be careful when we evaluate the limits. We're going to need to check the limit from both sides in order to determine whether the limit exists or the limit does not exist based on the behavior of the functions. That's what we're going to look at next. How do we think about vertical asymptotes? Now we're going to do this with algebraic techniques. So the first step is to try evaluating your limit with direct substitution. You're going to need to try direct substitution all the time. That's step number one whenever you have a limit. If you get 0 over 0 or any number divided by 0, it could be 0 over 0 or any number divided by 0 when substituting, there must be a vertical asymptote at that x value. To try simplifying your function, think about factoring if at all possible. So sometimes it's possible to factor and have one of your factors cancel, in which case you have a whole instead of an asymptote, makes your life a little bit easier. And finally, in order to figure out what's happening near an asymptote, you need to substitute a value that is near your desired x value to determine the value of your limit. One thing that we should note is that anytime you have any non-zero number, something, for example, like the number 4, divided by a number that is very small or close to 0, your answer is going to be either positive or negative infinity, depending on the signs of these values. So like this is a positive divided by a number that's close to 0 but positive, you're going to have a positive. A negative divided by a negative would make it positive, and then if one of these was negative, it would make it negative. We're going to go through several examples here to kind of go through this process. So let's say we were to give you this same kind of limit that we had at the beginning. But you'll notice that this time, instead of having the limit as x approaches 2, we have the limit as x approaches 4 from the right. If we were to try this problem, step number 1 would be to try direct substitution. Now, when I try direct substitution, I get 4 squared plus 4 minus 6 over 4 squared minus 6 times 4 plus 8. If I were to simplify here, I would have 16 plus 4, which is 20, minus 6, which is 14. And if I were to evaluate the denominator, I have 16 minus 24, which is negative 8, plus 8, which is 0. You are not allowed to divide by 0, but this is not indeterminate. Indeterminate would only be if this was 0 over 0. So instead, we have a situation where we have a number divided by 0, which means there must be a vertical asymptote near that number. The next thing I'm going to do is try factoring. So if I were to factor in order to simplify this limit, the limit as x approaches 4 from the right, the numerator factors to x plus 3 times x minus 2, and the denominator factors to x minus 4 times x minus 2. Once again, the x minus 2 factors cancel. So my new simplified limit is the limit as x approaches 4 from the right of x plus 3 over x minus 4. After you've factored, I think it's much easier to see that there's going to be a vertical asymptote at 4 in this problem. Now, if we want to approach 4 from the right, then what that means is that we're going to choose a number slightly bigger than 4 and plug it in. And when I say slightly, I mean very slightly. A number that is slightly bigger than 4 would be like 4.1. So if I were to plug in the number 4.1, I'm going to have 4.1 plus 3 divided by 4.1 minus 4, which gives me 7.1 divided by 0.1, where this is a very small number. Now remember, we arbitrarily chose 4.1. We could also have chosen 4.01 or 4.0001. Either way, this ends up being a positive, but a very small number that's positive. If you have any number divided by a very small number that is positive, then a positive divided by a positive makes my final answer positive infinity. And that goes back to this idea. Any non-zero number, like 7.1, divided by a very small number, so close to 0, is going to give you infinity. Now, if we wanted to evaluate the same limit, but instead we wanted to evaluate the limit as x approaches 4 from the left, I'm going to go ahead and just skip this step here because we've already seen that it's 14 over 0. I'm also going to skip the factoring step because we've already seen that the x minus 2's cancel. So what I'm going to do is just skip straight to the step where we're going to start to substitute in a number that's close to 4 but from the left. A number that's close to 4 but slightly smaller from the left would be like 3.9. Now that's what I mean by close. It can't be like 3. It has to be 3.9, very close to 4. So we would have 3.9 plus 3 divided by 3.9 minus 4, which gives me 6.9 divided by negative 0.1. Now, negative 0.1 is a very small number, but in this case, it happens to be negative. So because of that, we would get negative infinity as our final answer. Now we can confirm this by looking at a graph of this function. If we were to graph this function, it would look like this. You'll see that the x minus 2, there's a hole, which canceled, gave us a hole in the graph at positive 2. And there is indeed a vertical asymptote at 4, just like we expected with the x minus 4 not canceling. We can also see that if we were to evaluate the limit from the right side, this graph goes up towards positive infinity. And if we were to evaluate the limit from the left, then from the left side, the graph goes down towards negative infinity. So we can confirm the answers we got algebraically by looking at a graph of the situation. Let's go ahead and try a few problems where we need to evaluate these limits. Suppose I ask you to find the limit as x approaches negative 2 from the left of this function. If I were to do this, my first step would be to try direct substitution. When I try direct substitution, I get 3 divided by negative 2 plus 2 to the 4th power, which gives me 3 divided by 0. The fact that I have a number divided by 0 tells me there must be a vertical asymptote at x equals negative 2, because otherwise I would have gotten something indeterminate, like 0 over 0, if there was going to be a hole. So my next step would be to try to factor. There's really nothing here that we can factor, which means my final step is going to be to plug in a number that's very close to negative 2, but slightly to the left. If you imagine a number line with negative 2, slightly to the left of there would be like negative 2.1. So I'm going to plug in the number negative 2.1, which means I get 3 divided by negative 2.1 plus 2 to the 4th. Now, 3 divided by negative 2.1 plus 2 would be negative 0.1 to the 4th. And what we need to know is that when we raise 0.1 to the 4th power, this ends up becoming positive. So we end up with 3 divided by a positive small number. Now, when we have 3 divided by a small positive number, we're going to get a positive infinity as the final answer for my limit. Another example problem would be like number 2. Suppose we were asked to find the limit as x approaches -2 for this function. My first step again would be to try direct substitution, which means I would have -2 plus 1 divided by -2 squared plus 3 times -2 plus 2, which means I get -1 divided by 4 minus 6 is -2 plus 2 is 0. Because I got a number divided by 0, it tells me that there must be a vertical asymptote in the function. So my follow-up step would be to try to factor. If I were to try to factor this equation, I would have the limit as x approaches -2, and on the top I have x plus 1. I should organize my notes better. There we go. On the top I have x plus 1, and on the bottom I have x plus 2 times x plus 1, which the x plus 1's cancel. Now that's great, but it doesn't fix my situation here. I have 1 over x plus 2, and I'm still trying to find the limit as x approaches -2. So I still can't plug in my number because I'm going to have 1 divided by 0. To do this then, I'm going to need to check both sides of the limit. So first I'm going to check the limit as x approaches -2 from the left, which means I'm going to choose a number slightly to the left of -2, like -2.1, which gives me 1 divided by -0.1, which is going to give me -infinity. And if I try to plug in, and I've run out of room here, and I do apologize for that. So first I'm checking the left side, then I'm going to check the right side. If I try the limit as x approaches -2 from the right of 1 over x plus 2, a number that's slightly to the right of -2 would be like -1.9. So I'm going to go ahead and plug in -1.9, which is 1 divided by 0.1, which gives me positive infinity. Now, because these two limits do not agree, the negative infinity and the positive infinity, I would say that ultimately this limit does not exist because the two sides disagree. Now that kind of concludes our thinking about vertical asymptotes and limits with infinity. The next thing we're going to be doing is connecting end behavior and limits. So one of our learning targets was to look at the limit as x approaches positive and negative infinity, and this is where we're going to start to do that. When we examine what happens to a function as x approaches a very large positive number, for example, infinity, or a very large negative number, like negative infinity, we are examining something called the end behavior of the function. To examine this behavior using limits, we would look at the limit as x approaches positive infinity and the limit as x approaches negative infinity. Now, this can give us several different types of results. So we could have a function without a horizontal asymptote. If your function does not have a horizontal asymptote, then your end behavior is going to be what's called unbounded, which means it goes up, up, up forever, or down, down, down. If on this graph I was to look at the limit as x approaches positive infinity on the x-axis is here, which means I'm following the graph as far to the right as I can. If I were to follow this graph to the right, I would also be following it up towards infinity on the y-axis. So this answer would be infinity. Another example would be like this one where the ends go opposite ways. So one end could go up and the other end could go down. In this case, if I was to find the limit as x approaches negative infinity on the x-axis is to the left. And if I were to follow this graph to the left, it would be going down towards negative infinity. Now, we can also have a situation where we have functions that do have a horizontal asymptote. So this is an example of functions that do have a horizontal asymptote. You'll notice that instead of following the graph to the right and then the graph going up forever or down forever, in this case, if I were to follow the graph towards positive infinity, it's actually getting flatter and flatter and flatter and approaching the x-axis, which has a y value of 0. We also could, for example, have a horizontal asymptote that's not at 0. An example of that would be in this graph. If we follow the graph to the right towards positive infinity, the graph is still getting flatter and flatter and flatter. It's just getting flatter towards the value of 3, which means the answer here would be 3. If the limit as x approaches infinity, or the limit as x approaches negative infinity, is equal to a number, so not going up towards positive or down towards negative infinity, but actually equal to a number, like 0 or 3, then the graph has a horizontal asymptote at that number. If you find the limit as x goes to positive and negative infinity, and the graphs increase without bound or decrease without bound, going towards positive or negative infinity, there is no horizontal asymptote for that graph. Let's take a look at how we would find this algebraically. So we know that we can look at a graph and we can figure this out, but how do we do this without a graph? To evaluate the limit as x goes to positive and negative infinity, we're going to look at the highest powers only. And the reason we're going to look at the highest powers only is because x is approaching a very large number. So the highest powers take over the behavior of the function. We use those factors to write the end behavior function. It tells us about the end behavior of the graph, and since we know that x is approaching positive and negative infinity, it's telling us we want to look at the end behavior of the graph. Then we substitute either the positive or the negative infinity into this new end behavior function to determine the value of the limit. So for example, if I were to give you this equation and say find the limit as x approaches infinity, by seeing x approaching infinity, I always think if it's a very large number, I only want the highest powers. Now, the highest power in the numerator is the x squared, and the highest power in the denominator is the x squared. So I can find this limit by looking at the limit of the highest powers only, which is x squared divided by x squared. Now, x squared divided by x squared simplifies. So because I can simplify this, I'm going to go ahead and do that before I try substituting my value, which is, it simplifies to just 1. And the limit as x approaches infinity of the number 1 would just be 1. The reason the answer is just 1 is there's no place to substitute infinity. It's just always a 1. We can confirm this by looking at a graph of the function. If you were to graph this function, you can see that there is a horizontal asymptote at 1. So as x approaches infinity, it's going to be getting closer and closer and closer to that horizontal asymptote, which is 1. Let's go ahead and go through a few example problems so we can see how to do this when we truly don't have access to a graph of the function. For problem number 1, we want to find the limit as x approaches infinity. As soon as I see the limit as x approaches infinity, I think to myself, I need the highest powers only. In this case, the highest powers in this problem are x squared and x squared. So my simplified problem would be the limit as x approaches infinity of x squared times x squared. Now, once again, I can simplify this before I try substituting. So I would have the limit as x approaches infinity of x to the 4th. If I were to plug infinity into here, I would have infinity to the 4th power. And infinity to the 4th power is just infinity. For problem number 2, I want to find the limit as x approaches negative infinity. So again, I'm going to look at the highest powers only. In this case, the term with the highest power is 5x cubed. So the part of the function that I'm going to look at is the limit as x approaches negative infinity of 5x cubed. If I were to plug the negative infinity into there, I would have 5 times negative infinity cubed. Now, a negative cubed stays negative, and it turns out that negative infinity times 5 is still negative infinity. So that would be the answer. For problem number 3, if we wanted to find the limit as x approaches infinity, I'm going to say x is very large. I only want the largest powers. So the term on the top would be 3x squared, and the term on the bottom would be x squared. My simplified function would be the limit as x approaches infinity of 3x squared divided by x squared, which does simplify. So my simplified function would be the limit as x approaches infinity of just the number 3. Now in this case, there's no place to plug in infinity, so the answer is just 3. For problem number 4, if I wanted to find the limit as x approaches negative infinity, I like to think biggest x's make biggest powers, so 5x on the top and x squared on the bottom, which means I would have the limit as x approaches negative infinity of 5x on the top and x squared on the bottom. Now we can simplify this, so one of the factors of x will cancel on both the top and the bottom, which means I have the limit as x approaches negative infinity of 5 over x. If I were to plug in negative infinity, I would have 5 divided by negative infinity. And I like to think about this as if you have 5 pizzas divided into infinity of your friends, everybody only gets a very small piece of pizza. So because you're dividing it into so many pieces, the answer here is 0. For number 5, this is a slightly different problem. So it says limit as x approaches infinity of x cubed over 2 to the x. Now, there's nothing to factor here. And so, or there's nothing to really simplify here. The highest powers are the only things that are in the problem. And this brings up one of the points that is really important for calculus. This bottom function is what's called an exponential function because the variable is an exponent. And one thing that we should know is that an exponential function something like 2 to the x, will always be much larger than a polynomial. For example, x cubed, when x is approaching positive or negative infinity. So because of that, when we substitute infinity here, the infinity cubed on the top and the 2 to the infinity on the bottom, this bottom function will be much, much larger. So what we can do is we can imagine that this is really just a number divided by infinity. Ultimately, this infinity cubed is so much smaller that it just becomes a number. And because of that, our answer here would be 0, just like our answer here was 0. For the next problem, it's kind of the reciprocal of what we were looking at. So if we were to substitute in our negative infinity, we would have e to the negative infinity divided by negative infinity squared. Now, in this case, you're going to have e to the negative infinity, which if you imagine the graph of e to the x, as you go to the left towards negative infinity, the function actually flattens out towards 0. So what we would have here is 0 divided by a number. And again, this is a number because e to a power of infinity, an exponential function is so much bigger that it wins. So a 0 divided by a number would just be 0. Now those two problems are pretty much the trickiest that they get because it's very conceptual, but really the thing you need to know is that if you ever have an exponential function, that one takes over and wins. Doesn't matter what the other function is. All right, that brings us to the end of our notes. Thank you guys so much for watching, and I look forward to seeing you soon.